we're going to go ahead and start out with Jay from Dato, and I'm going to let him kick it off. Okay? Oh, by the way, my name is Mary. If anyone's curious.
Thank you, Mary. So good evening, everyone. My name is Jay. Today I'll be talking about crunching through 100 billion edges within minutes with SGraph. I'm from Dato. Dato is a young machine learning startup building tools and platforms for scalable machine learning that is easy to use. So I was actually very fortunate to be with the founding team. We founded a company in 2013 named as Graphlab because at that point we were the best. We're still the best doing large-scale graph analytics. But we changed our name to Dato in January this year because since then our product surface has expanded to tackle more data types and doing more machine learning stuff. It now can handle numerical data in tables, text data, and even image data in addition to the graph data. However, we have never forgotten our roots, and our strength in large-scale graph analytics. So today I will not talk much about machine learning, but mainly focus on graphs. So back in Strata in the Bay Area this year, I met with a couple of people from Common Crawl organization. They came to me and said, we have this huge graph data set. We published it in 2012, and yet not many results has been shown, has been done on this graph because not many graph analytics systems can handle that scale. So I asked them, how big exactly is your graph? Is this big, giant graph? It's at 3.5 billion nodes and 128 billion edges. That's pretty big, the first time I heard of it. And if you think of it represented naively in memory, it takes 2 terabytes. It's even, also it's 20 times larger than the Yahoo AltaVista web graph, which was the largest graph I have ever played with before this one. So I wasn't sure about the answer. So I looked up online to find out experiments about graphs on this scale. I found out this one. Facebook used Apache Giraffe on 200 very beefy commodity machines to compute PageRank, and on a graph with 1 trillion edges, which is an order of magnitude bigger than this. So you look at the throughput, it's about 20 million edges per second per machine. And I came back and did experiments on SGraph, which is our graph system, on a single EC2 instance with a little bit more RAM, 200 gigs. It takes 9 minutes per iteration to do PageRank on this graph with 128 billion edges. And if we measure the throughput, it's 200 million edges per second, which is an order of magnitude bigger than one PageRank has, the Facebook has. Okay, and so this is what I'm going to talk about today is the SGraph, which is our graph analytics system. Since this is an introductory talk, I will begin with what is graph and why should you care about graph? But I assume most of you will know this, so I'll run through quickly. So graph is a powerful mathematical object that captures relationships. And the relationships are ubiquitous, it's everywhere, so are graphs. So a lot of successful companies, they build their products, provide values on top of the insights extracted from graphs. For example, Google uses PageRank to rank the pages, and the Facebook recommend friends use graph between users, and Amazon recommend items you want to purchase, which is based on the graph between users and product. And PayPal can do some fraud detection based on the graph, transaction graph among users. So this is why we care about graph. And typically, how big are those graphs? Typically, it has like about 1 million. The size of the graphs varies. The number of vertices can be 1 million to 1 billion. And typically, number of edges is 1 or 2 orders of magnitude larger. So here are just a few examples of graphs, the size of the graph. the Netflix challenge, 100 million ratings, and about 500,000 vertices, which is combination of user and movies. The Twitter follower graph, as snapshot at 2010, has 40 million vertices and 1.4 billion edges. And of course, the largest graph dataset, Common Core 2012, has this 3.5 billion vertices and 120 billion edges. And given a graph, a goal of a graph analytics system often involves tasks like finding some important nodes, like finding influencer in a social network graph, infer some missing attributes, like labeling some nodes that could be spammers, or clustering nodes that finding communities. I have been working directly or indirectly on a few of the existing graph analytics systems. Started from 2010, I worked on Graphlab, the first version of Graphlab, which is a shared memory architecture which parallelized graph analytics algorithms. In 2012, we extended the system to a distributed setting and it tackles natural graphs with power law degree distributions. And Power Graph is still the reference benchmark to a lot of large-scale graph analytics papers today. And at the same time, Apple, from the same group, built the same idea on top of a single machine with external memory, which becomes extremely successful for GraphG.
Can you just quickly explain what power law degree distribution?
A graph with power law degree distribution means you have some nodes with a lot more edges than most of the nodes. It is very natural in the social graph and the web graph. Some web pages are way more popular, or like Justin Bieber has way more followers than I do, right? Than most of us sitting here. So that's kind of the degree distribution follows power law. Okay, and in 2014, the same Joseph Gonzalez from the same group went to Berkeley and implemented the same power graph idea on top of Spark, and that is today's GraphX. So I have learned a lot from building these kind of systems, and a lot of learning is going into the SGraph we are building today.
Excuse me. Hey, if anybody wants some beer.
Can I add one, please? So the most valuable lesson I've learned from the success of GraphG is that big graph does not necessarily mean big data. If you're talking about most of the graph analytics tasks, what does it mean? To represent a big graph is a lot less challenging than, it requires a lot less space or storage than traditional big data. Just to give you an example, a classic task like PageRank only requires 2 floating points per vertex. If you're taking into the context of the Twitter follower graph with 14 million edges, you can comfortably store it with less than 1 gig of memory, even representing naively. Also, 1.4 billion edges only takes about 20 gigs of memory or on disk. So it fits perfectly on my laptop. With some compression, you can easily achieve at least 5 times the reduction of the size. So that's the size of a big graph. If it's not that big and fits comfortably onto a single machine, why is it still challenging? Why are we still talking about it? First of all, a clean graph dataset does not come up naturally. This is what you would expect a graph dataset looks like. It is one table with all the unique IDs, integers, and another table with 2 columns having each row representing a source to a target. And that's it. However, in the real world, these IDs can be very long strings. To extract those relationships from logs or text and JSONs can be challenging. So this is what the real data looks like. And this is where you start from. Also, feature transformation and graph egress is as important as ingress. and they are equally painful because often the result cannot be stored in the graph forever. You need to take it out, put it into a table, run some more analysis, come back to the graph again. So most of us have heard this 80-20 rules for data scientists who spend 80% of their time cleaning the data and before they can get into any meaningful analytics tasks. This is even worse with graphs because doing data engineering on graph is very unnatural. People like to do it on table. But conversion between graphs and tables are extremely costly. So the first challenge we are thinking while we're building this SGraph representation is how can we make data engineering on graph more natural? When it comes to graph representation, if you have a computer science background, you normally think it as an adjacency list or a sparse matrix representation. But if you're data science doing data engineering or feature engineering, you want to think of a graph as two tables. Some data for a table for vertex data and a table for edge data. This table can sit in SQL or like in other pandas data frame or other representation, but abstractly it is table. So the left-hand side is about the structure of the graph, while the right-hand side is the metadata part of the graph. And we want our representation to facilitate tasks that on the right-hand side much more easier. So this is the graph representation of SGraph. It is just simply two tables, one for vertices, one for edges. There's underscore ID columns representing the structure of the graph, the vertex ID, and the source ID and destination ID of an edge. And the rest of the column are metadata associated with vertices and edges. Internally, we actually store these source ID and destination ID as pointers or row numbers into the vertex table so that we don't replicate the ID many times. This is very simple. What can you expect to do with it? Let me show you a quick demo running from my laptop. So we import Graphlab. Graphlab Create is a Python package that you can download and play with locally. And I have some raw data from a friend at CMU who was doing some tweets crawling. So this is the directory which contains the file he gave me. So people who have done anything with the Hadoop or MapReduce jobs can recognize this is obviously coming out of a MapReduce job. Each of the part is a text file. And there are about 1,500 files. And each of the file looks like something like this. So this is a retweet relationship. So Jefferson Stein retweets something from BBC News. And this is the graph we're going to play with. So first thing we do is we read it into a tabular representation called sFrame using this read CSV. Interestingly, we can treat this as a CSV file because it has a comma in it. But the reality is I didn't look at it. I just used read CSV and I realized what you get is something like this. So it has two columns with an anonymous name, and each of the vertex has an actual parenthesis on top of it, at the end or at the beginning of it. And we want to clean it a bit first. So let's rename these two columns with something more meaningful. So rename this to source and rename the second columns to destination. And we look at it again. By the way, it has 2 million rows, so it means probably about 2 million edges, right? So each edge is from one user to another, one Twitter account to another Twitter account. And it means that it has retweeted something from the other account. Now let's apply a user-defined lambda function, which just get rid of this pesky parenthesis. And we look at it again. you can notice that the apply almost returns immediately, that because it is a lazy evaluation, which I will explain later. And we can look at the end of the S frame, which will take a lot longer because the computation actually happens. So this is the clean, the columns after you clean up. And then because people can retweet from account multiple times, so we want to do a group by and then compute how many times a retweet happens between any particular pairs of accounts. And this is the result. And the aggregation result from 2 million rows goes to like 1.9 million rows. So most people only have retweet. Most pairs only has one retweet. We can actually look at the degree distribution of this count column. So you at least retweet once because that's presented in the data, and the the largest retweets count is 22, and 99% of people only retweet at most twice for a particular account. So this is nice. We understand a little bit more about this data. These are all done on the table, which we are comfortable with, and powered by this powerful S-frame tabular representation. If you're interested in looking at those anomalies who retweeted a lot more times, you can do a logical filter using syntax easy like this. Okay, now let's try to construct a graph. Put this edge data. So this is almost as clean as I showed you on the few slides ago. So we can actually put this into a graph. So the syntax is really simple. You add some edges, right? And you use the source and specify the source and destination field. It also returns immediately because of a lazy evaluation, which means you can add edges multiple times, and it only materializes when you query for it. So we look at this G, which is the graph we're interested in. And it should tell you how many edges it has, how many vertices it has, and what are the fields associated with vertex or edges.
So you're materializing this graph now?
Yes. Okay, has 1.9 million edges and 2.3 million vertices. Interestingly, it has more vertices than edges because the graph is extremely sparse. Most of pairs only have one edge between them. And we can look at the, so here's about the representation, right? Once the graph constructed, vertex is just a table and edges is just a table. And you can do the same feature engineering on these tables as I did on the graph as I did on the tables. And it will show up on the graph. So let me show you some example of the graph analytics task. So first task is about finding influential nodes in the social graph using a PageRank algorithm. So we call this PageRank.create on graph G with 20 iteration, and it returns a model object which we can inspect later. So 20, okay, so it finished in 7 seconds of 20 iterations on this graph with millions of edges. And the one table we are interested in this result is this PageRank table. It's an S-frame with each vertex's PageRank. So for each vertex ID, you get the PageRank of the vertex. Delta just shows you how well it converges at the last iteration. Okay, naturally, next step is to ask who has the highest PageRank. Anyone here want to make a guess? On Twitter? Fine, I'll show the result. Right, so just some simple analytics, you can identify important nodes on a big graph. We can also look at the distribution of the page rank here. This is also like a power law like degree distribution. Most people only have like less than 1 page rank, and some people have, very few people have extremely high page rank, like these accounts, right? Okay, the next task I want to present is infer some missing attributes on nodes. I know there are a split of Star Trek and Star Wars in the universe, so, and also shows up in this graph. So I will just put some initial label on vertices whose ID contains Star Trek. I will label it with 0. Whose ID contains Star Wars, I will label it with 1. For the rest of the vertices, I will just say, I don't know. Okay, and I apply this init label function and create a new column and assign back to the vertex table of G. Now, if you look at G.vertices now, it should have a new column called label. Most of it is none because who would put these strings in your ID, right? But we can actually look at those accounts who are being assigned with some initial labels. So these are the accounts. This is a logical filter operation. This expression evaluates to a Boolean array, which we use to filter out all the rows which contain Star Wars. So these are the Twitter accounts with the Star Wars in their ID. So here, I'm going to do one thing, which is flip the direction of the edge. Because label propagation works where if I retweeted someone, the influence is from that guy to me. Whereas for PageRank, if I retweeted that guy, it's because I respected that page or I like that account. So it's my mask to that. It follows the mask follows from the retweeter to the guy being retweeted. So in this label propagation algorithm, we just flipped the edge around, which is very easy. You take all the vertices from the previous graph, take all the edges from the previous graph, and just flip the source field and that's the field. And this is the new graph, which is exactly the same like before with edge flipped around. Now we're going to run this label propagation algorithm. The detail doesn't matter. What it will do is it takes all the nodes with initial labels and apply those influence along the direction of the edge, and then try to label those, try to assign a probability of each of the nodes being a Star Trek faction or a Star Wars faction. So it's done. Similarly, it returns a model with a label as the S-string, and we can actually look at those who have initial labels. Their predicted label is forced to be the same as their initial label by nature of the algorithm. These two columns are the probability of a vertex being a label 0 or probability of a vertex being labeled 1. And we can add the result from the previous analytics, which is a PageRank, to the labels data table. Now we have extended this table with some label information, and the previous PageRank information, which we can use to do further analysis. Here, what I want to do is I want to select all those vertices who has more than 0.15, the baseline PageRank, and who has not been initially labeled. And I want to sort them according to their probability of liking Star Wars, and then sorted by their PageRank. And this is the result. You can see some Twitter accounts that like Disney picked, Jedi Domer. So these are the users who has been applied a new label. Okay, if you're interested in following any of these, come talk to me at the end of the talk. So the building block of this SGraph is called S-frame, which is a compressed columnar architecture built on top of using external memory architecture. That means it is stored on disk. It is made for easy feature engineering. Creating columns are easy, transforming, delete edges, deleting columns, moving columns around, drawing, filter, sort, group by. And then it has this lazy evaluation feature, which means it builds up all the operations until you want to see the final outcome. Does it materialize a chain of operations? And before it does the final materialization, it actually went through query optimization, like a database would typically do, to make sure it does the most efficient. It does it efficiently. It also can store very rich data types, like besides integer, double, these. It can also store string and images, and list and dictionary on each column. So it is very useful for data engineering. And it's very scalable. The largest S-frame we have experimented with has 1,000 columns and 1 billion rows. And that amounts to 1 trillion numerical values. And yet we can run it at interactive speed, like what I did before. It is very usable. It comes with a bunch of nice utilities, like the best CSV parser ever, which does automatically type inference of columns, even within quotes. And you can easily get statistics of each column and visualize it, as I did using Canvas. So here are just a recap of some typical S-frame operations that you would like to perform normally. Like normalizing a column, apply a lambda function, arbitrary Python lambda function. It will capture the value just fine. And create a column using multiply two columns together like you would do in MATLAB. So in summary, SGraph is a unified representation with seamless transition between graph and tables that makes data engineering on graph significantly easier. Okay, in the next part of the talk, I'm going to discuss about how do you program a graph algorithm that can run in parallel. I will explain to you how we implement this PageRank, and once you understand it, you can extend some graph algorithm or write your own graph algorithms. So one thought about this is to think like a vertex when you program a graph. So if you look at the PageRank of user I is equal to a constant plus a weighted sum of the PageRank of its neighbors. You initialize every vertex with PageRank 1 and update this computation run this computation on each of the vertices in parallel until it converges. So in pseudocode, it looks like a function which takes vertex I, initialize some temporary variable, perform a weighted sum to gather the PageRank from your neighbors, and apply the changes to your vertex at the end. And in the outer loop, you just run this in parallel on all the vertices and until it converges. However, it has a thinking like a vertex or programming using a vertex update function has a strong requirement on the system or the representation, which is when you want to perform any vertex update on V, it requires a quick lookup or easy or constant lookup of all the edges that have V as a destination node. And this is just for PageRank. For general graph algorithm, you will also like to access the vertex, the out neighbors of V, right? So these are all the edges with V being the source. If you look closely, these two are the same data source, but represented or grouped differently. So it presents a challenge where you either store it twice, which means you read from two places and write into two places, or you keep the vertex edge table in memory so that you can do random access, which is also very expensive in terms of memory footprint. So Power Graph solves it by going distributed. Okay, we partition the graph, store a subgraph on each of the node, on each of the machine, and each machine loads the subgraph entirely, including all the vertex data and edge data. So GraphG invented some very clever algorithm called power sliding window, which groups edges cleverly on the disk so that each iteration you can load a subgraph of including vertex and edges into the memory with minimum disk I/O. But ultimately, they both require storing the entire subgraph in memory, including vertices and edges, which makes them less scalable. And they also require complex data structures to keep down the memory footprint. So how do we address this challenge while keeping our simple graph representation as just two tables? Well, if you look at this think like a vertex again, the vertex program, the inner loop of the vertex program really breaks down into a separate computation applied on each edge. And the key observation is that most of the time, it doesn't really matter if these computations on each edge is run at the same time or should be run together for each of the vertices. It means you can arbitrarily interleave these edge functions, and then the result will still be the same. So this leads us to our approach, which is think like an edge. We call it the triple apply abstraction. So given an edge with source, edge, and destination data, you just apply a function. This PageRank triple apply function simply adds a take the destination PageRank, increment it by the source PageRank times the weight on the edge. And similarly, while not converged, you just run this in parallel on all the edges as one iteration. And at the end, you apply to the vertex data constant shift. So see this in animation. I load in, I grab an edge, get the vertex data on both ends, apply this function, throw the edge away. I don't have to keep anything in memory. It's entirely running in a streaming fashion. So from think of like a vertex to think like edge, using a simple triple apply abstraction with streaming edge model, we can keep the simple graph representation and make it much more scalable, because you can dedicate all your memory to store the vertex data, which is critical for the graph computation. So today, the triple apply function can be used on multiple levels. If you're doing simple prototype, you can write a triple apply function in Python and try it on a reasonably large graph on your laptop. If you care about performance, you can use our C++ SDK to write a triple apply function in C++. Also, if you look at our source code, all the graph analytics algorithms are implemented using triple apply function. So it is pretty powerful to capture a wide range of graph analytics algorithms. However, so far, my assumption is that you can load the entire vertex table into memory, but sometimes they just won't fit, right? There are cases where you want to run matrix factorization with 1,000 latent factors. That means you're storing 1,000 numbers with each vertex instead of 2 numbers. There are times where we store images associated with each vertex and just want to compute the similarity between 2 images. And each image can come with thousands of features as well. So this can be feasible if we assume all vertices can be loaded in memory. And at Dato, our first design principle is graceful degradation to make sure things always work, even if it doesn't fit in memory. So the solution is simply to partition the SGraph layout from one table to multiple tables using a very simple layout. So having a vertex data table here, and I have an edge data table here. I'm going to cut the vertex data into p disjoint sets. In this case, p equals 4. And then I will cut all the edges into p square partitions. And with the constraint that the partition ij on the edge data contains and only contains vertices from partition I to partition j. So in this case, the vertex data from partition 2 and 4 plus the edge data as frame 2, 4 defines a subgraph that you can load that you can use to apply graph computation on. And then you just load the next subgraph, which may be like 3, 4, and then you unload this vertex partition 2 of the memory and load 3 back in. So this requires swapping the vertex data a little bit. And we use this clever traversal ordering called Hilbert Curve to work across the edge partitions to minimize the vertex data swapping, disk I/O. So to accommodate large vertex data, SGraph uses a simple partition layout that scales. It comes with a trade-off, though, because swapping vertex data is costly sometimes. And some algorithm just works much faster if you can assume all the vertex can be kept in memory. So if you still remember that thing, the lesson that big graph is not necessarily big data, it can be a lot more smaller. And look back to the common crawl graph again. 3.5 billion vertices, and the task is PageRank. Why don't we just keep it in memory? It only takes 60 gigs of RAM. And then in these days, you can easily get a server with more than 100 gigabytes of RAM, or just use EC2. So the pretty fast tip we applied to speed up PageRank on this graph is just simply keep vertex data in memory. It avoids swapping, it knows straggler, minimizes the disk I/O. So a lot of graph analytics algorithm can be done with vertex data in the memory. And this is our benchmark result on this graph using a single Amazon instance with one SSD, 200 gigs of RAM, 32 cores, costs less than $3 an hour. So the degree count takes 500 seconds, PageRank is 9 minutes per iteration, and we've also tried to connect the components and the label propagation as well. So the lesson is at system level, we ensured graceful degradation as our first principle. But for some algorithm, we expose knobs that allows users to tune for their hardware for the best performance. So SGraph is just this fast, scalable, and easy to use graph analytics data structure. It comes with a bunch of tools that you can off-the-shelf graph analytics algorithm that you use, including PageRank, label propagation, connected components, and so on. Use SGraph in you can do seamless transition between graphs and tables, which makes data engineering very easy. Using think like an edge principle, you can write your own graph program very easily. And we apply graceful degradation as our first design principle to make sure even vertex data doesn't fit in memory, you can still run it, even on laptop. And when we have control of the assumption of the system, we optimize it heavily. So today, this SGraph I just presented is available as open source Dato core with the AGPL license. The Dato core contains the core data structure, which is S-frame and SGraph, and it comes out with all the graph analytics toolkits. And we also provide the Graphlab Create as a licensed software, which provides a lot more than graph analytics, including solid machine learning fundamentals, advanced machine learning tools, including deep learning, visualization on S-frames, distributed asynchronous job execution, and predictive service, so you can quickly move from inspiration to production. So this is the end of my talk. Thank you, and we are hiring. Yes, please.
Do you offer any JVM bangings to your Graph Spark? You mentioned C++, Python.
Yes, the current Graphlab Create is built entirely in C++ with a Python language front end. I don't see it a hard limitation for a language binding as a front-end language. In fact, we are considering R as our next step, but of course there are also a lot of requests on JVM side. But normally, we have this predictive service, which is once you created a model, like a graph analytics model, recommender model, you push it to the cloud, and we have all the client libraries, including Java, JavaScript, Python, you can use to access the model that data scientists just produced. Thanks.
Isn't that something about streaming the vertex algorithm or something like that? Streaming edges? What is that? Can you explain that?
Oh, it means when we do graph computation, it's not about edges are constantly being added while you're doing the computation. It's when you take the graph and you don't load the entire edge into memory and just load the edge one at a time. That reduces memory footprint and can dedicate most of the memory to the vertex data to keep things faster. Yes?
You mentioned a bottleneck that arose when swapping vertex data.
Yes.
When do you swap vertex data?
Could you repeat the question?
Yes, the question is, the major bottleneck is swapping the vertex data. And the question is, when do we swap? So if we go back to this slide, we only load a few of the edge partitions at one time. And for each of the edge partition, we require 1 or 2 vertex data to be stored in memory. So when we move the edge, move from the subgraph to 4 to 3, 4, we naturally unload vertex data 2 back to disk and load 3 back in.
I see. And that's the swapping that takes a while.
Yes. When the vertex data is big, or when you have a lot of vertices, like in Common Core. Yes, please.
So what I found most interesting in this talk was that when Graphlab started out, it was all about proving that you could do scalable graph analysis and spread it across the cluster and what. And now you're going back to, let's do single machine, lots of memory, much faster. Does that mean that the scalable approach doesn't work? You shouldn't do graph analytics in a cluster, you should focus on single machine?
That's a good question. The question is, when Graphlab started out, it was a distributed system to ensure the best scaling. And now I'm presenting this on a single machine, which is a lot more scalar than before. The question is whether we are constrained in a single machine, or is single machine the best practice for graph analytics, or is there still hope for distributed? Of course, there are still hopes for distributed, and we learned a lot from building a distributed graph analytics system, and we apply a lot of learning into pushing a performance of a single machine. And then we are actually considering going distributed again with, when you combine distributed with external memory, that's when you get the best scaling. No more questions? All right, thank you.